Am I on here? Yes? Okay, perfect. Thank you very much, Katie. So as Katie said, my name is Scott Stender, and I'm here with
Alex Vidigar.
And we are both with ISEC Partners. Our talk is Concurrency Attacks on Web Applications. And you might ask, well, who are you and why do we care about listening to you or this topic? We are both security consultants. We work with ISEC Partners, and Microsoft is one of the clients that we can name. We are out here a fair amount of the time. But we also see a rather wide variety of the industry, different people using different technologies or using your technologies outside of this environment. And so we hope to bring an external perspective to a lot of the things that drive your guys' efforts. We are based in Seattle and in San Francisco. So the core idea of this talk is that web applications or web application programming environments encourage programming styles that result in concurrency flaws. Now, that's not to say that you cannot create a web application properly that is nice and thread safe. By no means. We did not. We actually had a joke slide in here which we took out. But as kind of a riff on our on the security industry as a whole, we had thread jacking. Is your grandmother safe? Everybody is going to die. You must worry about your applications and go write them right now. Really, that's not the point of what we're talking about. What we want to emphasize is that the environments that programmers are working in make it very difficult for them to use patterns to be thread safe, very difficult to find flaws, and hopefully we can identify a few patterns for helping you create safe software and also test for it. And then for those of you that do have a lot of background in concurrency and thread synchronization and all that, I hope you'll find it interesting how we illustrate the use of purposely vulnerable applications using .NET technologies and IIS and SQL Server, and you get a little perspective on how people are consuming your applications, and maybe that'll help drive things going in the future versions. So there's our introduction. With that, I'll turn it over to Alex for a brief introduction.
Okay, I'm going to try to move quickly. Hopefully, can you all hear me first of all? Yes? Okay, super. Okay, concurrency in the context of this is just processes being executed simultaneously in an application. Obviously, not getting done simultaneously if there is only one processor, but essentially multiple things going on at the same time. So if you look at what does concurrency mean in a single application, that might be that an expensive operation gets put off a little bit, while inexpensive operations might be servicing the user, letting them know that, hey, you're still there, things are still going on, but I'm going to go talk to a database, go write to disk or something in the meantime while that user is idle. And that is a good programming tactic because it allows you to do lots of things at once, allows, like I said, expensive things to be put off until the user isn't going to require that feedback. It allows your application to be scalable. So all in all, concurrency is a good thing. However, things do get a little bit more complicated as your application uses multiple threads. You're running that application on an operating system, which also has multiple threads changing between the applications running. Maybe you're using another application like a database. The database is also using threads. So you have this huge complexity of threads going on. You're not necessarily sure when they're going to be executed, if they're going to be executed at the same time, or in the same order each time, and it creates a complicated problem that can introduce concurrency flaws in your web application or other applications. But we're going to focus on web applications for this talk, of course.
So what does it take to handle multiple threads of execution? Now, this is from the programmer's perspective. Obviously, you guys might be the people who are actually implementing this on the OS perspective, but from the programmer, first you have to have a way to define a thread. This would be the thread-based function. That is the start of when you spawn off a new thread, an independent unit of execution within a process. And it's upon the programmer to define that thread and its well-behavedness. In order to get that well-behavedness going on, you have to have a way to manage those threads. You have to start the thread, suspend them, exit them, all that good stuff. So you have to have operating system support for managing these threads of execution. You have to have a way to share data between them. In the Windows architecture, you have all threads can interact with the same process address space. So you can address memory directly, or you can also use the thread local storage. Then you also have to have a way to synchronize access between them, and that is where you have either programming level or operating system level synchronization methods. That makes it so that the individual threads of execution, who you can't predict who's going to execute when, are able to synchronize data access so that people don't step on each other. So it sounds complicated if this is not the first time, if this is your first time hearing about thread management, and it is, and it sounds complicated because it is complicated. Designing, implementing, and testing, scalable, concurrent, thread-safe applications is very difficult and the subject of a lot of very academic and also practitioners' research. Actually, just yesterday, a friend of mine sent me a link to something on ResNet where a PhD candidate from UIUC was out here, giving a presentation on her research into automating the identification of concurrency flaws, again, within a single, native process. Not so much what we're talking about here today, but there are whole tomes written on this, and of course, most of that is going to be outside the scope of what we're going to discuss.
Okay, so bringing it back into our scope, we're talking about web applications. Mm-hmm. So if we look at what a simple, basically what a web server or web application needs to do, it needs to take requests, it needs to figure out what that request is, see what other resources that request is for, grab those resources, and then provide them back to the user. And this is a situation where threading is awesome because instead of having one person occupy your whole program to get that request, figure out what needs to get done, you can have that single thread kind of in a more complicated design. A simple web server design is like you have a basically a one thread that handles all the requests to the web server. It might handle them, give it some kind of identifier, and then pass it off to these worker threads that are going in the background. And that allows multiple people to access that web server and allows much more throughput, scalability, like I mentioned earlier. If you just have one program with a main function, if it has to do all of those things, it's obviously going to block. You're going to have lots of versions of it to service more people. So once you've created a multi-threaded environment, which probably most web developers don't have to do because that's handled by the actual web server itself. But once you have created that multi-threaded design, you can process lots of things at the same time, do all those expensive operations, and hopefully have a good performant application that can meet your requirements for servicing and without locking up. So, like I mentioned, most web developers don't actually have to worry about that so much because there's a framework involved. With Java, the ones that we looked at a lot were struts, and obviously .NET applications is that framework that allows web developers not to worry about it so much. And that's kind of brings us to the next slide.
And once again, Alex has laid the foundation. We'll talk about the programmer's perspective of web application frameworks. Now, there are a large number of web application frameworks used today and historically since web programming became a little bit more common in the mid-90s. But the ones that are most in use today, the ones that we see a lot of times with our client work, are the .NET-based and also J2EE-based frameworks. And so for representative examples, we worked, as Alex said, in the .NET, ASP.NET environment, and in J2EE with the struts-based environment. Now, both of these are somewhat common in that they expose a object-oriented model where you don't have to the programmer doesn't have to do hardly anything to manage thread pools and context and parsing HTTP or anything else. Really, your job is to implement a function as the web application developer of today. In ASP.NET, that is, you implement page load or any number of other event handlers. And the framework is responsible for calling that function. So you could think that the goal of these frameworks is to free application developers from the drudgery of having to manage thread pools, connections, parsing, all that other good stuff. Really, you want to have them focus on the simple implementation of business logic. And this is great for developer productivity, and it's great for getting things that that are common tasks that are also error-prone in the development off of the plate of the content developer and let them focus on just their jobs, being creative. Now, a couple of the side effects of this is that when all you have to do is simply implement a function, a lot of the complexity of those things, of managing thread pools, of parsing requests, gets abstracted away. Really, all you have is you implement page load, and within that context, you have your HTTP session. If you want to save a variable that is going to be stored session side and keyed off of the user's session ID, you just go to the session map and you say, session key username equals something that I pulled out of the request. Request parameters username. That would take a piece of data that is off of the HTTP request and store it server side so it can be keyed off on subsequent requests. It's all great. I mean, that one line of code, where it refers to two different objects, the session and the request, are abstract away a huge amount of complexity of thread pools and all that good stuff. Then all you have to do is simply say response.write, whatever you want to do, and send the response away. So sometimes abstraction is wonderful for developer productivity. Sometimes it helps for the developers to actually know what's underneath there. Like, let's say there is a shared piece of data that needs to be synchronized, and the developer might not never know it's there. That's the kind of thing that we're worried about, and that's what we mean when we say maybe the development environment encourages these types of flaws. So as a quick demo, actually, if you want to
while Scott gets the demo ready, this first demo is really simple. It actually doesn't show us a whole lot. What it does is it gives us an opportunity to show the test tool that we have, which basically takes a lot of requests to web server and tries to do them all at the same time. In this particular run, I believe we do 20 requests every 5 seconds, trying to get them as close to the same time as possible. It also shows a very quick look at a very basic application, the traditional bank application that allows you to transfer funds from one account to another. And also it'll give us a chance to look at how the web application and the web server processes are handling this pretty rudimentary example. So go ahead, Scott.
Yeah. 2 caveats also is I am not a graphic designer, as you can see from my wonderful web development here. But it is straightforward and to the point. It's good engineering. But the idea is that we have this very simple online bank. Simply by going to the default page, you're able to be logged on, and behind the scenes, it's doing all the password management and all that good stuff for you. And then we're able to say that we have 2 accounts. We have account ID 1 and account ID 2. Both of them have $1 million in them, and this page allows you to do the canonical concurrency test of transferring funds between accounts. So if I specify a source account of 1 and a destination account of 2, and I transfer $1, it will take its sweet time and error out on me, of course. That was the other caveat I have, is that I believe in live demos, which has bitten me from time to time. We did this talk at BlueHat, and 1 out of the 4 demos died on me, but the other 3 were successful. So let's hope that we get 100% this time. There we go. Your transfer was successful. Our total balance is $2 million, and so this is the standard page that you will see upon transferring funds in my hacky bank. Now, however, the reason why I counted up your total balance and displayed that was because when we do a bunch of testing later, we're going to view the total account balance as the key asset that we want to make sure is protected. As a single user, I should not be able to manufacture or remove money from the world. I should be able to just transfer money between my 2 accounts. So when we go back to the default page, we'll see that indeed I've moved $1 from account 1 to account 2, and we can move it backwards. And we still have $2 million, and we are now back to where we started. Now, another thing to show here is just exactly what the baseline properties of our database server and our web server are. Now, here I have perfmon, and I think most people in this room should be quite familiar with it. I've tracked 5 different attributes of the system. First is % of total processor time, so the overall CPU load at a given time, and that is the highlighted one there. Next up is the % processor time for the database server, and you can see that there is very little. A couple of seconds ago we had the smallest little uptick when it had to transfer those funds and log in. We also have the current thread count, the number of active threads inside the SQL Server process. Then we have the % processor time for the worldwide web service worker process. So this is the actual process that hosts the web application we're interacting with. We can see that, again, it's using very little processor. There's a couple little blips from the request we did a few seconds ago. And then finally, the thread count for that worker process. Right now, it's standing at about 19 threads or so. What we're going to see is, as we stress the server, all these different parameters, all these different attributes will vary through, will increase, decrease, and and respond to our stress. So for one quick request that will cause no damage to our server, we're going to run this little Python script I have called sync test. What sync test will do is it will spawn the number of threads that I say to spawn, and as Alex pointed out, it'll be 20. So effectively, we're going to simulate 20 individual clients, and it's going to make requests every 5 seconds in a burst. All 20 threads are going to try to synchronize with one another to make those requests. And the idea is, by doing that burst, we're going to encourage a little bit more of threads stepping on one another. Now, what I'm going to do right here is just hit the log on request. So it's going to each thread will log on 5 times in quick succession. So it warns me you're about to do 100 requests, no biggie. All the threads start. If we go back over here to perfmon, we will see that actually this is a very low cost operation. We can see that the processor time for the worker process does a little spike. And it'll come up again every 5 seconds or so until all the threads are done. And there's our next one. Oh, look at that. One demo down. Everything is working so good so far. All right. So that's the general idea, and when we're done with this, we'll see all the threads print out that they're exiting, and we get a little response here where we show we can say that we can see the the request time for each one of these requests, the hash of the response, and so I just took the HP response content, which includes your total balance is $2 million, and I include it in there so that we can see any changes. Then we can look at the request and we can look at the response here, and sure enough, if I click on there, I can see what that thread actually got, and it said, you were able to log on, and here's your current balance, no big deal. So that is our test site. We're going to revisit it a couple more times. Now, what happens when all those threads execute simultaneously on something interesting like transferring money? Well, the answer is it depends. Anytime you have a piece of shared data, and by that I mean anything from a session variable, potentially, to a global variable in the application, to, let's say, a database, which is something that is a centralized data store that is going to be accessed by multiple threads on the front end, you're going to have to somewhere synchronize data or access between those, or else maybe something dangerous could happen. So now, again, if we go back to the framework is trying to abstract away and make it so that people can be productive and do the safe thing, the secure thing. In a lot of ways, ASP.NET does a pretty good job of, anytime it can, making things be safe and secure by default. But of course, you also have to make a functional system, and you have to leave some things up to the programmer. Now, here's a little sampling of guidance given to developers for the J2EE side of things. The first quote is actually the one that inspired this talk. A few years ago, I was doing a review for a struts-based system, and I hadn't worked in struts before, so I pick up the big O'Reilly 300 or 400-page tome on struts programming, and amidst all this guidance on actions and validators and all this other good stuff, there was one little, exclamation mark on the side. By the way, developer, keep in mind that HTTP session is not synchronized. And it goes on to say things like, you may experience severe problems. It's up to the programmer to protect shared resources. Of all the things that you can tell a struts programmer, and this was the older version of struts, it's actually changed a little bit recently, but at the time, of all the things you're going to tell a struts programmer about functionality, you're going to leave out one little thing. By the way, session variables, not synchronized at all. Better watch out for that, with no prescriptive guidance on how to respond to it. Same thing, you go down the line with a bunch of the different Java guidance. If you look at the struts 2, you see that action objects are instantiated differently, so their behavior in a threaded environment is a little bit different. Same thing with Hibernate and Java. The Java language neither prevents nor requires detection of deadlock conditions. Basically, this is a whole big punt to the developer. Now, I didn't add anything for .NET on here simply because there was very little guidance. Once you knew what you were doing, you could maybe find, search the internet and find some guidance on what happens when I try to access something in an HTTP session. Is it safe? Is it not? If you go to MSDN's page on it, it doesn't say anything. Go ahead. I see you all have your computers. You can check right now. There isn't any specific, do I have to worry about this or do I not have to worry about this? The response is, it depends. You have to dig around there. Turns out, .NET by default, if you use its session management mechanism, it will serialize all requests for a session ID so that it is somewhat safe to access a session variable. But that's not clear. It's something that you have to do. And if you are somebody who splits time between, say, Java programming, .NET programming, and PHP programming, you have to have a little context switch, figure out what you're doing right. So consider an online bank's transfer funds feature. Here is a little bit of pseudocode for that. We accept a source account object. That account would maybe have the account owner in it, the account balance, a bunch of other things that you would associate with a bank account. Same with the destination account, and then the amount that you want to have transferred. So the first thing I'm going to do is I'm going to pull out the source account's balance into a local variable, source amount. I'm going to check to make sure that that amount in the source account is greater than or equal to the amount requested for the transfer. Then I'm going to, if that's okay, then I will go ahead and deduct the amount from the source account balance and add that to the destination account's balance, and I'll return. Now, in a valid type of implementation of this, we check for some other things like, does the requesting user actually own the source account? And is the user, transferring a negative amount? No, we'll leave those things out. They're not really representative of the specific thing we're trying to show here. But this will do for now. Now let's see how synchronization and lack thereof can affect such a function. We have here the worst diagram of all time. We have thread 1 on the left, thread 2 in the middle, and then a little bit of data about what thread 1 and thread 2 think the different balances have within them. So thread 1 starts off and it says the source amount in my local variable is equal to the account's balance, and then it gets preempted. No more execution for you for now. Operating system transfers control over to thread 2. Thread 2 is doing the exact same thing. It goes through and does the entire transaction. It says, okay, source amount, now that I'm still $10. I haven't changed that. I'm going to go ahead and check to make sure that I can transfer $1. Sure, I can. The source account balance on the, again, thread 2 is now $9. The destination account balance is now $11. I return. No more need for do processing on that thread. Operating system gives control back over to thread 1. Then it says, okay, if source amount, which is still $10, is greater than or equal to amount, okay, I'll allow that transfer to go through. Now I'll adjust balances. The source account balance is now equal to $9, $1 off of what I had before. Never mind that somebody else went and adjusted that balance. And then the destination account is now $1 more than what is already updated. So now I have a total account balance of $21. $9 in account 1, $12 in account 2. So this would be a lack of synchronization leading to manufacturing money out of the air, which only the Federal Reserve can do these days.
So once again, just to go over the demo while Scott gets it ready, we're basically going to demonstrate that same problem where we have our version of the funds transfer, which has a lot more checks in it. If we went through functional testing, you'd see the tests for all the nasty things like negative values, bad input, all that good stuff. But what it doesn't do is it doesn't protect against concurrency. And that's just an intentional design. We're going to run our sync test against it, do lots of concurrent requests, and we're going to demonstrate how those requests can get corrupted data at the end.
And I am sorry for those of you in the back who can't see the specific code. Don't worry, it's not the most important thing to be seen. I will describe what's going on. But you can see that our transferfunds.aspx page has 3 different versions of transfer funds. We'll go through all of those in time. But the first one we're going to try is just a plain old naive transfer funds. And that is over here in our account.cs file. And sure enough, that's pretty much the pseudocode that we had there before. We check a couple of account ownership things we didn't do before, but it's honest, I assure you. There's nothing terribly contrived. No sleeps in the middle of it. So as we saw before, our current account balances are still $1 million and $1 million. And now if we run that same tool, except for instead of doing just a login request over and over and over again, I'm going to spawn those same 20 threads. First thing the thread's going to do is going to log in and get a unique session ID. And then each thread is going to start transferring money back and forth as quickly as it can for 5 individual, five individual requests, and then it will exit. Now, why is it important that I log in first? I gave a hint about this a moment ago. Any answers here? Yell them out or grab a microphone. There we go. I heard it way back there. I said a moment ago that ASP.NET will queue all requests for a given session ID on a single thread. That way, if I did 20 individual threads and just started hammering on them as hard as I could, all of them would just go in the same queue, and we would have a very perfectly synchronized application. By logging on each one individually, I get a unique session ID so that queuing doesn't happen, so I can go and do some attacks. So here we go. We start them off. My 20 threads are kicked off, and they're running as fast as they can. We move over here, and we see that already we're starting to get a couple little bumps on our worker process CPU time. Also, our thread count, which was at 19 for a baseline, has now gotten as high as 24, now 25. We can see that as it's getting stressed, it's increasing the worker thread pool to be more responsive to these, the higher load that the CPUs or the service is experiencing. And then we get finished here. Sorry, a little active content, owning myself. If we look at the first response, we see the total balance remains 2 million. After a surprisingly small number of requests, only 4 down, we see a change. Sure enough, we're down to $1 less. Then we get back up to 2 million. If you see that 604 there, it takes just a moment to get back up to 2 million. A little bit later on down the road, we get back to, it looks like 199, and then down here, we have up to 2 million too. Great. So if you're the attacker and you want to make money for yourself, then you're doing pretty well. You might stop. It's kind of like playing blackjack. Now, with this rather naive implementation of both the attack script and the server, it's actually going to, we've noticed it's about 50-50% as to whether you'll end the day down money or up money. If this were a real-world attack scenario, we might time our request, we might, have a combination of loading the server plus specific timing to try to encourage, again, probabilistically, making money or destroying money as we see fit. So at the end of the day, after all those requests, and you can see that I have about 100 or so down there, we can go back and check our live request. And we see that after all that work, we're up $1. So there is the naive implementation. I hope that you all now agree that I'm not just a complete liar, that sure enough, if a not terribly contrived implementation of a front-end web server and a back-end database can be predictably manipulated using just a remote client, and this is all local client and VM-based, but it doesn't take a whole lot of work to stress the server sufficiently so that in a non-contrived case, you can cause these concurrency flaws to occur. And in order to get ready for the next demo, I'm just going to reset balances here. Oops. Okay, we're back to 1 million. And with that, we go back to the prezo. So concurrency flaws as a class or attack are commonly known. I did not coin the term thread jacking for our talk today or any other jacking suffix. These things are named under a whole bunch of different subtopics: race conditions, time of check, time of use, state attacks. It really is. People will often apply a more specific identifier to the class of concurrency flaws or synchronization flaws, depending on the specific scenario involved. But there's little guidance in the area of web applications, as I mentioned before. People are giving just little asides. People are not really giving a whole lot of information on what is, thread safe and what is not. And it really is up to that, again, overworked function implementer who's just trying to focus on logic to figure out all of this information. So hopefully we can come up with some better ways. And also, as those of you who have either developed or tested highly scalable applications, you've probably run into that one really awful threading bug that was really hard to reproduce and really hard to find and really hard to fix. And so that makes it very difficult to also find these flaws, is that the developer who's making a web application and doing some bench testing is almost certain not to come across these. I mean, here I have 20 clients that are regularly pounding on the server in order to find, trip these types of attacks. So that makes them subtle, makes them hard to find. So I think with that, I turn it over to you.
Sure. So we mentioned some things that might introduce concurrency problems with with your application. But when does a concurrency problem become an actual security risk? Or a security flaw with your application? When it kind of depends what that piece of data or what that information is being used for. Obviously, if you're dealing with financial institutions and that information is being created or destroyed, the continuity of that system is very important. And that can be a security problem, in particular if probabilistically there's a method that allows you to create money. But obviously, if money is being destroyed and it's your money, you can be concerned just as well. You also might be concerned with a one-time use event. So, for example, if you can download a piece of music one time based on some purchase, and you can concurrently download that one piece of music multiple times, then obviously that's going to be a control that a concurrency flaw might allow, the multiplication of some product that you don't want to be multiplied. You also might consider if there is, basically what it comes down to is continuity of your data. And if it's being used to control things, either time-sensitive things or assets, that it's important to iron out those problems, to determine through either reviews or tests whether they're going to be problematic sections, and basically focus on if what it comes down to is a state. Is that if you can modify a state of some data, and that state is going to determine some fork or flow of your process, that portion of it needs to be examined for concurrency issues. So that is kind of the gist of where concurrency flaws might end up into security risks. Okay, so we mentioned that you take our frameworks, which are making these applications a little bit easier to make for the developer. They're not going to have to worry about some of the little intricacies of taking this thread and spawning it off and managing all those threads. Like Scott mentioned, .NET does a pretty good job of synchronizing on the session, and Java or J2EE does a pretty bad job about it. They basically just punt that and say, hey, we're not going to synchronize all of our things. You might run into some concurrent modification exceptions, but other than that, you can really create a big problem with concurrency. But if you look at your application and you're diligent about it and you're actually thinking about it, you can do a lot to protect it. But oftentimes we don't just create a single application. We create applications that talk to other applications. Or we create an application and that one application is deployed in a distributed fashion. There's possibly multiple servers running that single application. Maybe those servers are in different data centers, and then it becomes synchronization of that information or that flow. It becomes a little bit more complicated. And then we take that situation, maybe our application depends on an external resource like a database. And well, now we need to synchronize with our application and on that database. And then we add multiple applications on that one database. And then we compound it again. We say, okay, well, we want lots of applications and lots of databases. It's basically the problem which is solvable on a very, very small level. Maybe you can solve it simply with your application. Once you started to scale and create larger, more complex systems, then the predictability and the controls that you need to put in place become equally more complicated. So I'm going to go through kind of a simple evolution of what you might do with resolving this problem at the application layer. I'm going to use the term layer a lot. I'm not talking about the stack, the OSI stack. We're just talking about either the application or the database, essentially, or external resource. So if you look at our simple first design, basically it just queried the database. It said, okay, here's my information. I'm going to update it, and then I'm going to update the database as appropriate. And as we pointed out, that has problems because you don't know when each thread is going to go through that critical section of code and what time. So why don't we just check for information that might be dirty? Maybe right before we update that, we go ahead and double check, make sure that another process on our application hasn't updated it. If not, then go ahead and update the database. That's good. It's narrowing the window a little bit. It might make the occurrences of concurrency flaws to be less, or maybe harder to produce, but it's just closing the window. It's not closing it. It's making it smaller. It's not closing it completely, basically. And then the same thing, why don't we check really, really close? Like, why don't we do an update and a check at the same time, best as we can? Basically, no matter how narrow you make that window, it's the possibility of the threads being switched out still there. There's still going to be a potential concurrency flaw. So forget about it. Why don't we just take a big stick, whack it, say, let's just put a global lock on that particular part of the application. We're not gonna allow other people, other processes to go in and modify that data because we want that to be secure. The data is the most important part for us. So we're going to lock. Once we're done with that piece of data, we've updated, we've checked that it's fine, we'll release that lock. It's a question mark up there because it's kind of not a delicate solution there because you've basically, with a global lock, you've reduced the solution to something more like the single process web server that takes their requests, says, okay, hold on a sec, I'm going to go figure out what you need. While other people come in, you say, wait, I'm busy over here. You've bottlenecked your application to that one lock, and it's not going to have the serviceability or the quality assurance of your users that you're going to want, and what really is demanded by a web application. So take a big broad stroke, and you take it, and you be a little bit more delicate about it, and you can create a context-specific lock. Many of you probably read about these in books and gone through classes, etc. This is a little bit more delicate of a situation where you put a lock around the user and the particular piece of data so that that one particular user, regardless if they're logged in, they're going to have that piece of data locked. And then other users can access their own version or their own piece of data that is equivalent to that, and they're not going to step on each other's toes because that protected piece of data is locked by itself, and the web server or web application as a whole can continue to service other requests. So we did just that. We'll try to move quickly so we don't run out of too much time, but
10 minutes ago. All right. Sorry, I've been a little bit worried. The last time we did this, we had a full 15 minutes more, and so we're going to have to rush through a little bit of the slides here. Please do ask us questions afterwards if we glossed over anything you'd like us to explain in more detail. But if we fix this thing at the application layer, I hope you all will agree that that would probably work for us. We have a single application, a single database. As long as we get everybody nice and orderly up front, then it'll work out pretty well. So what I have is an equivalent implementation of transfer funds, except for one thing I pass in there that's different is I call it TX lock. It's just an object. It's something that is going to be static per this class, the transfer funds class. That means that everybody who interacts with this page is going to be interacting with this same actual object. And then I'm going to synchronize on that. So if I go over here to the account thing here, we'll look down here, and it's exactly the same function, except for the first thing I do is I say lock on transaction lock. I do a little bit of error validation that's not going to be temporally modified. I check to make sure the amount is proper, but then I lock immediately, and I keep locking until I'm done. So if I build that, and sure enough it succeeded, and if I publish, it'll go off there. Again, the craziness of the live demo, building and publishing right before your very eyes. When we update that, it'll take a second for the web page to come back since we just published a whole new version to it. So it's going to be waiting. And there we go. We see our worker process is back here, and he's working hard, so I think we are good to go. And sure enough, this web page came back, and we're back with a fully operational website, hopefully now safely locked. So we run that same exact tool again. it goes through, it starts executing, and if we look at the baseline of this here, we see that the performance is still pretty decent. Yeah, we're seeing the spikes that we saw before, but none of them are terribly bad. It's not like we're pegging the server as a result of this lock. It's not like we're, it looks like we're deadlocking or having any big problems. It actually seems like it's working pretty decently. Looks like we're about to come up on our number 5 spike here, and so these should be exiting any moment. And I hope you'll believe me if I say that during this whole time, our total balance stayed exactly where it should have been at $2 million, and we had no problems. And sure enough, our hash is exactly the same all the way down. So ordering things on the way in did a pretty good job of making this, of solving this problem, except for, as Alex pointed out, oops, where's my slide? As Alex pointed out, that's at the application layer. If you have 2 applications that are load balanced across a single database, we're right back where we started. If we do it at the application layer, then it's only the amount of control is going to be scoped specifically to that framework, to that application. We're going to have to synchronize across applications or back at the data store if we're going to do it right. So with that,
okay, you might see the similarity between this, the database layer, and the previous, which is the application layer. So I'm going to kind of skip down to the bottom. The quick solution might be to just axe everything and say, all right, we're going to send it all through one database connection. That way we can rely on some of our ASP.NET synchronizations, and hopefully that all of that stuff gets executed in a synchronized or a serial fashion. Once again, though, you've kind of created that same problem where you have limited all your resources down to one bottleneck, and it's not going to have the performance that you want. So obviously, the solution is to allow the database, a lot of things in the database are designed in order to facilitate the locks. So essentially, you create locks on the database called database transactions, and that allows you to remove the locks from the application layer, move it down to the database, and the database is going to lock rows based on the user, based on the access, and provide a similar type of synchronization. So I believe we have a demo for
okay. Yeah, and so database transactions, if you have worked with these before, you'll recognize a little acronym, ACID. They are atomic, consistent, isolated, and durable. That means that they are exactly what we want. We'll lump them together. They will all stand as one or fall as one. So that sounds perfect to us. We're going to run a demo. So I have, going back to the transfer funds example here, I have transfer funds TXN. Sure enough, when I go down over here, I see that I'm doing pretty much the same thing, except for the first thing I do is when I create my database connection, I create a transaction object, and then I associate that with my command, and then I use that command to carry out all of my SQL commands. And then down at the end, what I'll do is I'll say, if everything works out pretty well, then I will say commit the transaction. And if I have any exceptions, I'll say roll back the transaction. That way, if anything goes wrong, it all backs out. So this, just like the last one, it should work out great, right? We understand the architecture. We understand that everything is going to, lock properly. So it should be, maybe we'll even skip this, but it's worth showing you anyway. So we've published. We still have exactly the same amount of money in our bank. And now we run this little sync test here. Sure enough, we go over here. We should see the CPU popping up any moment here, but it's not doing a whole lot. Now, we did just enable transactions, and so the database is in charge of managing the locks, and so it's not going to be as application-specific as if we'd done it at the application itself. So maybe we're going to get some deadlocks. Maybe we're going to have some problems. We can see that the thread pool went up through the roof. It's right up there at 32 threads. It's almost as high as I've ever seen it. So the front end, the web page, is really trying to hammer on the database. The database is saying, hold off, buddy. I'm taking my time on this. But we see, and there's the database threads. They're doing the same thing. They're all working hard, but not a whole lot of CPU load. That's one of the things about managing the transactions is that by pushing this down the layer, or down the stack, you lose some of the control, and you might hit conditions that are unsavory, like deadlocks. But at least the same amount of money should be in our account. So let's just go ahead and hit me. Whoa, $2,014. How did that happen? I just saw that. And go back to my slides here. Database transactions are atomic. They're supposed to all stand or fall together. How is it that after just running that tool, I found that I made myself $14? Well, that's not exactly what we were looking for. Now, who's a SQL Server dev, a database administrator out there? Which one of these ACID properties? You got multiple choice, four options. Which one of these might have been my mistake in my development environment? Anybody? Isolation. I think I heard it right there. Isolation levels. Isolation levels are the hint we give the database saying how much are these transactions supposed to be separated from one another. And they range from chaos, which acts as exactly as it sounds, all the way up to snapshot, which basically means I'm going to take a whole bunch of the data out of the database and manipulate that and put it all back down in one big dump. And so you go, the default in SQL Server 2005 and with .NET, if you use a SQL transaction API with no optional constructor, or optional data into the constructor, is read committed. That means a transaction that is executing will go ahead and go forward with the transaction, but any data that it reads is going to only be data that is committed by its peer transactions. Now that's great, you're not reading bad data, but that doesn't mean that you're not starting down a transaction if somebody else has already started when reading the same data. What we want is full isolation. You do not start until I'm finished, and we want to be able to put those in one long line, like say serializable. So there's our problem. We had an isolation level that was insufficient. So if we say begin transaction and we pass the isolation level of serializable, and actually in this particular case, in this very limited scenario, repeatable read would work just as well. But we're going to go safe on this one. And actually we can see my database is not very, or my web server is not very happy after all that deadlocking, taking a little while. But actually, since we are running low on time, let's go ahead and finish up the slides, and you'll have to trust me that that when you put the serializable in there, what happens is it does protect the integrity of the data, but at the cost of really horrible deadlocks. It goes down from maybe an average of 8 requests per second on the demos I've shown thus far, down to about 1 or 2, because basically as soon as 20 hit, they all deadlock on each other, and then they have to wait for one of them to have a deadlock timeout before we have any progress. So first of all, it takes forever. Second of all, you almost never get your actual transfer through, and you've introduced a pretty nasty denial of service condition onto your server. If as one client I can make your whole thread pool get focused on managing deadlock timeouts, then that's pretty great because nobody else can get in. So at the cost of data integrity, we've introduced deadlocks and denial of service. So how would we fix it in this particular case? Well, integrity at the database layer is an obvious win. That means if somebody else comes along tomorrow and creates a new application that manages my account balance, customer service application rather than my online bank, well, the database being the sole arbiter of, yes, the data has integrity is a good thing. But we also want to make sure that people are lining up and being orderly about making those requests so that we don't have deadlocks. So what we would recommend in this case is, since we can't change the schema, we can't reduce the isolation level, which would be the things you do for deadlock prevention, having a combination of serialize the application access to make sure that these corner cases are handled. When people are trying to do a bunch of transfer funds against their own accounts over and over and over again, that should be handled orderly, but then the transaction integrity should be enforced by the database. Now, there is no general case fix. You have to look at the specific environment, the specific database, the schema, all the other good stuff, and find out what is unique about that. Now,
okay, another thing to consider is what your data is being used for. Like I mentioned, it's important, in particular if it's a control. But if your data needs to be created, read, updated, or deleted by multiple users, then that's a constraint that you need to look at. If it needs to be only accessible by one person at a time, that's another constraint. If there is a problem with access, if those people accessing the data need to either be informed immediately if there's a change, or if for example, if you just are listing accounts, does it matter if those accounts, the balance of it changes? Maybe that's not necessarily important. So you have to look at the whole life cycle of your piece of data look at the requirements for usability, look at the access requirements, and then kind of make a determination of what you can afford to lock, what you can afford to synchronize or not synchronize, and then that'll help you identify areas of your code or areas of your design that might need to include more concurrency type protections. And as you can imagine, if you can imagine some variety of way to implement some type of data manipulation that has or doesn't have some type of concurrency flaw, well, basically, if you can imagine it, it can be done or can't be done. So it's not like it's a very small problem space. If you ask two people to program something, most likely they'll come up with something different. And of course, there's going to be different ways to protect a particular critical section of code. You might have to also consider whether that application is going to be standalone, whether it's going to rely on other applications like databases, whether it's going to be distributed, whether you can rely on operating system controls to do the locking for you. I guess...
Yeah, I think that's about it.
Yeah, I think that covers this slide. But basically, you need to look at what are all your resources, what are the ways you can control it at the database, at the application, and figure out what's appropriate for your distribution.
Yep. All right. Finding concurrency flaws. Now, we've gone over this a fair amount during the talk, a little bit more than we had planned for, so we can just zip through these slides. The idea is if you're going to find concurrency flaws, you can go through the formal type of review that Alex just mentioned, where you identify your data, you identify your, the users of that data, you identify the requirements of it, and then you do a formal review of everybody involved. Now, that's the way you might eliminate it, and if you look at the academic literature, that's a lot of what they talk about. So once you identify that, you can maybe build some tests. You can throw 5,000 requests at something you think might be a problem and profit. But really, as Alex pointed out, the technologies are a whole lot of different things are involved. You can't just simply read the code and say, hey, they don't have a lock-in here. They might well have transactions handled somewhere deeper in the framework. They might have it handled at the operations layer. So it is non-trivial to figure out exactly where this is happening as an external black box reviewer. You really have to have a lot of involvement from the development team. If you test it, this is the particularly difficult way to find concurrency flaws because you can't have a single fire and forget test. I can't run my 20 clients running 5 requests each in a every 5-second burst and say, okay, I still had $2 million in my account, life is good. Because it could be that the window was extraordinarily small and I didn't have enough stress on the server, I didn't do enough requests. All I can do is prove for the existence of them, not the absence of them. And that makes it very difficult. But what you can try is, first of all, stress the server. Things are more likely to occur. You're more likely to preempt a thread in an important transaction while the server is under stress. So that's key. You want to make sure you have enough client stressing. You might even have a couple of clients doing nothing but running expensive requests against a server that have nothing to do with concurrency flaws, but that generate enough of a CPU load to hook in there and do bad things. You also want to consider what assets you're protecting. Here, we had accounts that were owned by a single user, so we want to have that user be logged in multiple times to try to manipulate their own accounts. And as I pointed out earlier, ASP.NET has a goofy thing and a great thing where it will queue things based off of the session ID, and so you have to do things like log in first with each of your test clients and then start stressing in order to get that. If I had just started early, started naive, and made a bunch of requests and given up, then clearly, by only having one login, then clearly I would have missed a rather important bug on this site. The tool that we showed here, sync test, is actually just a very simple Python tool that spawns threads and runs clients, and then circulates on requests. But once I clean up the code a little bit, it will be available on our website if you want to play with it. And
yeah, we just wanted to thank you for inviting us out here to talk. In particular, we'd also like to thank Jesse Burns and
Brad.
And Brad Hill. Brad's probably even out here. Man, that's insulting. But we'd like to thank you both for your input and review in the process. So thank you very much.
All right, and there's questions and answers. Thank you.